Okay, so as I promised, and this way we're going to cover the example for the open loop and a closed loop system. So we start first with the open loop system. We're going to go through the equations once again, and I actually advise you to write down this equation on your paper so you can use it later for doing the solution. So we said once again that the open loop positioning system is operating without any verifying of the actual position of which is going to be equal to the specified position. Instead of that, we're going to turn the lead screw with a certain number of the steps, and each step is going to representing a certain angle for the lead screw. So to turn this screw, we're going to use a 7 motor, which is going to be driven by a series of the electrical pulses generated by the MCU to rotate the step angle of alpha. Okay, so now this will be the first equation. We're going to have alpha is equal to 360 degree divided by the ns, where the ns is the number of the steps we have for the motor. The angle of the motor shaft rotation is going to be a factor of the number of the pulses we send to the shaft and to the motor and the alpha value. So the AM is equal to the alpha multiplied by the MP. Now the rotational speed of the motor shaft or the RPM value we have for the motor shaft is going to be equal to 60 multiplied by the alpha multiplied by the frequency we have for the driving motor and divided by 360 degree. And M of course is going to be in RPM. So we said that we're always going to use a reduction gear to reduce the RPM because we don't need to have a high velocity for the motor, but we're going to need a high torque. So to do that, simply the gearbox is going to be used. So something like the following. This is shaft one, and this will be the shaft two as an output. We're going to have two gears. The first gear here is going to be quite small, so for the bad drawing, and the other one is going to be large. So the large gear is going to provide a lower RPM value for the output shaft. So we are going to have the N for the motor here and the N for the screw on the other side. Okay. Now the reduction value is the RG. The RG is, for example, if the NM is going to be 4, the output is going to be 1. That's mean the output RPM value is 1/4 of the input value for the RPM. Now we go further, the angle of the rotation and the rotational speed of the DC screw is going to be reduced by this gear ratio. So the angle of the motor is going to be equal to 4 times, for example, of the RG value multiplied by the angle of the DC screw. Same thing for the RPM. The RPM of the motor is going to be whatever the ratio multiplied by the RPM for the DC screw. The linear position of the table or the x value, the distance that the table is going to be moved from position 1 to position 2 is known as the x. The x is going to be a parameter of the pitch value for the lead screw and the angle of the rotation we have for the lead screw divided by 360. So the x is p multiplied by the ALS divided by 360. The NP, or the number of the pulses we are going to send to the motor, is going to be equal to 360 degree multiplied by the RG multiplied by the X divided by the P, which value multiplied by the alpha. And this can be rewritten to be the RG multiplied by the number of the steps we have on this motor multiplied by the angle of the DC rotation divided by 360 degree. The velocity of the work table is going to be equal to the RPM for the DC screw multiplied by the pitch value. The RPM of the DC screw is equal to 60 multiplied by the frequency divided by the number of the steps multiplied by the RG. Finally, the frequency can be calculated with any of the following equations. Now we go to the example 34.1. Uh, this is going to be for the open loop. Once again, from this equation, we said that we have a stemming motor, a 48 steps angle. So this will be the NS value. The output of the shaft is going to be coupled to a lead screw with 4 to 1 gear reduction. That's means we're going to have 4 turns of the motor shaft for each turn of the lead screw. Now the RG is given as 1, as 4. The lead screw pitch value is 5 millimeter. So the P is equal to 5 millimeter per revolution. The work table positioning system is going to be driven by lead screw. The table must move for a distance of 75 millimeters. That's the X. From its current position at a travel speed of 400 millimeters per minute. That's the V. Find the how many pulses are going to be required. MP. The motor speed, NM. The pulse frequency, the F. Okay, so we need to find this parameter by using the previous equations we had earlier. So we start the solution steps. First, to move the distance x equals 75 millimeters, this screw must be rotating through an angle, ALS. So the x is equal to the pitch value multiplied by the ALS divided by 360. In this equation, the x is given, the p is given, and 360 is a number. So the ALS is the unknown. So I can rearrange the equation to find the value for the ALS. Okay, now we are on the next step to calculate the ALS. 360 multiplied by 75 divided by 5. Okay, sorry. So the angle is going to be 5,400 degree for the screw to rotate in order to move for 75 millimeters. So with the step angle of 48 for the motor and the gear reduction of 4, we can simply calculate the number of the pulses to move the table to 75 millimeter, which is going to be given by the following equation. Number of the pulses is equal to the gear reduction multiplied by the NS multiplied by the ALS. Now all these three values are known. 4 multiplied by 48 multiplied by the 5,400. And thus we are going to find that the number of the steps is going to be, the number of the pulses is going to be equal to 2,880 pulses. Here we can find a simple method to do that, something like using logic. We're using a lead screw. We're going to move 5 millimeter for every 75 revolution. We need to move for 75 millimeters. So we're going to have 75 divided by 5 millimeters, and this will be the number of the revolution required to move at 75 millimeters, which is equal to 15 revolutions. Now each revolution of the screw is going to require 4 revolutions of the motor, and therefore we're going to have 60 revolutions are going to be required by the motor. Of course, 4 is the reduction value. The motor has 48 pulses per revolution, and it's need to move for 60 revolutions, and thus we are going to have the total number of the pulses required for the 75 millimeters is going to be 48 multiplied by 60, which is 2,880 pulses. Now we need to find the lead screw speed corresponding to the table speed of 400 millimeters per minute. Now, when I say the lead screw speed, we need the RPM value for the lead screw or the N for the lead screw. The original equation we have that the feed rate is equal to the RPM value multiplied by the pitch value. Rearrange this equation, we will find that the RPM is going to be equal to the velocity of the table divided by the pitch value, or 400 divided by 5, and this will be 80 revolution per minute. So the motor speed is going to be 4 times speed faster than the lead screw. That means the Nm is going to be equal to the Rg multiplied by the NLS. Now the NLS is 80 revolution per minute. The RG is 4, and thus we're going to have that the LM value is equal to 320 revolution per minute. Finally, we need to calculate the pulses rate or the frequency. So the frequency equation is going to be the RPM value for the motor multiplied by the stepper number for the motor divided by 60. Now we have the NM is 320, the NS is 48, and divided by 60, and thus we're going to have that the FP is equal to 256 hertz is, sorry, just keep moving. Uh, the FP is going to be equal to 256 hertz. Now we're going back to the second example for the closed loop portioning system. We said we are going to use the same equations, but in this system we're going to get the feedback from the DC screw to specify the movement of the motor. To do that, we're using the uh, light encoder. So a common feedback system using any numerical control system is going to be the optical encoder, rotary encoder. The equation describing the operation is going to be the same, but it's going to be analogs to those, digital to those of the analog using for the open loop system. The basic optical encoder equation is going to be first finding the alpha value, which is the angle between the slots we have in the disk. Alpha is equal to 360 divided by the number of the slots we have for that disk. Once again, this will be the optical disk. It's going to have multiple slots. Just to find the angle between these two slots, again to divide 360 by the number of the slots we have here to find the value for the alpha. So each time the light passing through the slot is going to be sensed by the photocell and give me an output signal 1. We count the number of the pulses, and that's what we do with the case of the optical encoder measurements. So to a certain number of the angular rotation of the DC screw, the encoder generates a number of the pulses going to be given by the ALS, which is the rotation in degree for the DC screw, divided by the alpha, which is the angle between the slots. Or I can extend that because you know that the alpha is equal to 360 divided by the ns, so I can extend this equation to be in the new form. The pulse count can be used to determine the linear x-axis position of the work table by factoring it in the DC screw pitch value, or the x is going to be equal to the p and p divided by the ns, which is the pitch value multiplied by the pulse number divided by the slots number. Or I can rewrite it down to be the P multiplied by the ALS divided by 360. Now the feed rate is going to use the same equation. The feed rate is going to be equal to the RPM, the RPM for the DC screw multiplied by the pitch value. The NLS is equal to 60 multiplied by frequency divided by the number of the slots. Now let's see the other example. We have a numerical control work table. It's driven by a closed loop positioning system consisting of the servo motor, a DC screw, and optical encoder. So even if we didn't mention the closed loop here, we said that we have a servo motor and the optical encoder means that we're going to have the closed loop. The DC screw has a pitch value of 5 millimeters and is coupled to the motor shaft with a gear ratio of 4:1. The optical encoder generates 100 pulses per revolution of the DC screw. Okay, that's when we have the NS here is equal to 100. The table has been programmed to move for a distance of 75 millimeters and the rate of 400 millimeters per minute. Determine how many pulses are going to be received by the control system, the MP, to move for 75 millimeters. Now find the MP. Find the pulse rate, the FP, the frequency. Find the motor speed, the N. Now we start this solution test, find the MP first. So we remember that we have that the equation for the x is equal to the following. The x is equal to the MP multiplied by the pitch value divided by the NS. So we can rearrange the equation to find the value for the MP here. Now here the x is known, the NS is given, and the pitch value is given. 5 for the MP, 5 millimeter per revolution. The x is 75 millimeters, and the NS is equal to 100. Now we 100 pulses, of course, per revolution. So we can substitute these values, and we're going to find 75 by 100 divided by 5 is equal to 1,500 pulses is going to be required to move for the distance of 75 millimeters. Now, the pulse rate corresponding to 400 millimeter per minute can be obtained as the following. Now, the feed rate is given, the pitch value is given, and I can find the NLS by rearrange this equation as we did in the previous example. Now we need to find the frequency. This will be our first thing to be done. So the frequency is going to be equal to the FR, feed rate, multiplied by the NS, number of the slots, divided by 60 multiplied by the pitch value. Now in this equation, we know all the parameters. The FR is 400 millimeter per minute. The NS is 100 pulses, and divided by 60 multiplied by 5 millimeter per revolution. And thus we're going to have that the value for the FV is equal to 133.33 Hertz. Finally, for the least secure rotational speed, we're going to use, we can use actually this equation directly. Okay, or we can use the equation here with after rearrangement to be the feed rate divided by the pitch value. The feed rate is 400 millimeter per minute divided by 5 millimeter per revolution, and the answer is going to be 80 revolution per minute. That's for the least screw. Now the motor speed is going to be 4 times as the I don't know why we have the FA here, as the RPM value for the least screw, and then we're going to have 4 multiplied by 80 is equal to 320 revolution per minute. This will be the final answer we need to have for this example. Okay, if you have any question, we can come back to me, and also I think we're going to have another question during the tutorial session we're going to have.